Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, I'm going to tell you about CrashSafe. So kind of for the first third of my talk. Then I'm going to tell you about two papers I've been working on, so more research-oriented, on exceptions and information flow control and on testing non-interference with quick check. And then I'll discuss a bit about future directions. So since one of the papers is due in like 24 hours, I didn't get much sleep. So if I kind of stop responding, you could reset me or something. So the CrashSafe project is a big project by research team terms. We are 40 people, somehow almost evenly split between industry and academia. Most of the academic people are at Penn. Most of the industry people are at BAE Systems, one of the defense contractors, British Aerospace. You might have heard about them. It's a DARPA-funded project under a big umbrella program called CRASH, under which also some folks here at University of Cambridge are funded, and also many people in the US. So the goal of this project is to redesign a significantly more secure architecture, so a new computer, without having any sort of backwards compatibility constraints. So this is kind of great opportunity. And we are doing redesigning language, system, and hardware from scratch. So we have language people, systems people, and hardware people on the project. And we are working together to make this work well. And as a secondary goal, more like personal or for the more formal people there is a goal of verifying that we really got something more secure. We really got something secure. Well, whatever the notion of secure means for a whole computer. More focused, we are looking at mostly at the security of the operating system. So I made a break because it's an operating system if you look at it from the hardware perspective. It's a runtime system if you look at it from a language perspective. So you might have heard that computers today are really insecure, and you might wonder why. And one of the reasons for this is that they were designed really long time ago, when hardware was really expensive and performance was the driving factor in making always hardware run faster and faster and faster. Security was never a concern. However, hardware is now abundant. We had many orders of magnitude increase in hardware capacity. So this is a logarithmic scale, and it's like the usual thing you see when you talk about Moore's law. And today's systems were designed kind of around this time. Yeah? While since then, there have been 1, 2, 3, 4 orders of magnitude increase in hardware capacity. So hardware is no longer a problem now, but are we using that hardware to solve today's security problems? Well, not really. Or how much of it are we using it for that? Are we using 10 to the 4 or 5 to solve the security problems? So we want to do a redesign targeting security by taking ideas, from where I see it, mostly cool ideas from the programming language level, and applying them also at the systems level and also at the hardware level. Well, other people on the project see it differently. So we are interacting, taking good ideas for security and sharing them across the layers of the system. And some of these ideas, which I like, are on this slide. So we want to have type and memory safety enforced not just at the high level, but enforced all the way to the hardware. And we want to have, so that we get something like basic abstraction all the way to the hardware. And we want to have fine-grained protection by an access control and an information flow control mechanism that work on individual values at the language level and on individual words in memory at the hardware level. So I'm going to return to all these things. And to make it all more fun, we want to base all this on verification in the broadest possible sense of the word, which includes testing. So I'll spend like one slide on each of these layers, language, system, and hardware, and give you just what I can give in a slide about them. There's lots of details I cannot give you, but you can ask or you can talk to me. So the language is probably the least surprising from where I stand. It's more like a testing ground to try out ideas which we later port on to the other layers. It's a type and memory safe language, but dynamically typed. And it has dynamically checked contracts so that it recovers a bit of the niceness of types. It's a functional language with state and concurrency. It does message passing communication, so no shared state between threads. They just communicate over channels. And it has these built-in fine-grained protection mechanisms. So this is the new part. I mean, up to now, Scheme I guess, has that. So it has security built in. It has security labels attached to each value. Things like this value is public, this value is secret. And then it has dynamic information flow control to track these labels through the computation and to taint secrets, to taint values that depend on secrets also as secret. And then, based on the same labels, we do access control. And this gives us an even more powerful attacker model than for information flow control. So if you're untrusted code and you don't have clearance, you can't even touch a value. You cannot branch on it, you cannot compute with it, and then try to use side channels or things like this. You have to be completely polymorphic or parametric in that value. You can pass it around, but that's all you can do. So this is the access control. And then we have a novel exception handling mechanism. And the second part of the talk will be about that. Now, the runtime or the operating system is simple. It has a scheduler, an allocator, and a garbage collector. It has channels which are used both for inter-process communication and for communication with devices. So like infinite size buffers which resize automatically. And it has, well, this dynamic information flow and access control, as a protection server, which I'm going to talk about. We call this sometimes a zero-kernel operating system because this has a TCB that's even smaller than a microkernel. In particular, this is not monolithic. So because a microkernel would contain things like paging and things like that, while this protection mechanism for is more lightweight than that. Also, the thing is compartmentalized, so broken into tiny pieces which have the least privilege they need to operate. So the scheduler can schedule threads but cannot, say, forge a pointer, while the allocator might need to forge a pointer or to do some fancy things with pointers. So in the end, even if one of these components of the operating system gets compromised, even then you cannot do more than what that component could do on its own. Maybe if you compromise the scheduler, you can bring the system down, but you can still not read everybody's secrets. Okay, so this is about the operating system. As for the hardware, I think this is where the funnest things are and most novel, because at the hardware level, all the instructions have a well-defined semantics and abstractions are enforced. We have fat pointers, so you can't write out of frame bounds. You cannot do buffer overflows, jump to libc, stuff like that. Because we also have dynamic types which prevent you from forging pointers. For instance, you cannot turn arbitrary integers into pointers, which means pointers are unforgeable capability as they are at the high level in a safe language.
You're saying that
yes.
A pointer points to a patch of data along with its size, and the pointer says how big the thing is, so that you can't access out of bounds. Is that right?
Well, so
the hardware supports that.
So with each pointer, there is a base and a bound.
Okay, fine. So then, in order to make such pointers, how do you do that?
By allocation.
And is the allocation in hardware?
No. So there is a privilege instruction which can forge pointers, but the privilege to run that instruction is only given to the allocator.
Okay.
And no other piece of code in the system will ever have that privilege.
So if you compromise the allocator, it's game over.
You can forge pointers, but that's maybe not enough to mount a full-fledged attack. You might still not be able to turn an integer into an instruction, for instance, which might be necessary to do a buffer overflow.
So who assigns privileges? Could you compromise the privileges?
So this is the next point. So okay, the one after the next point. So I come to it. We have lambdas, so closures at the lowest level, and we have a protected call stack at the lowest level. And we have authorities and gates, and I think this is, to answer your question, we have a notion of authority which are first-class values, even at the hardware level, but most of the times they're not really used like that. But they're used with something we call gates. So a gate is, you can think of it as a system call. It's an authority-changing lambda call or whatever, function call. And the nice thing about it is that first, with the gate mechanism, you don't play with the authorities as first-class values, but you just create this gate, pass this gate to untrusted code. And the only thing the untrusted code can do with this gate is call it. And when it calls it, it's like a system call. It takes one instruction, as opposed to what it takes on normal architectures. So we have very cheap system calls, which means you can really break things into very many tiny authorities or many tiny protection domains, and then give each protection domain the least amount of authorities it needs to do its job, because it's very cheap. While on modern hardware, the most you can do is like, I don't know, 4 rings or something, and nobody even uses that.
It's a single instruction. The system call on most modern hardware is also a single instruction, but that doesn't tell you anything meaningful about performance.
You mean because you have to flash pages and things like that?
Well, multi-cycle operation that involves TLB churn and register churn and various other things on either side. So what sort of performance relative to a normal function call your call gets?
Not any more than a normal function call. There can still be cache locality there can whenever you jump, there can be, especially on long distances, there can be locality prices to pay. But that's all.
Do you still have to flush the entire register set if you don't trust the thing on the other side, or do you have some mechanism for saying you can't access these registers from the other side of the call?
We do have some mechanism. I don't discuss it though.
It's getting a bit confusing. We've got authorities, gates, labels, fat pointers. It's hard to know what all these things are at this stage. But you're going to tell us.
Well, no, not really. So you better ask now. If you,
Can I ask a question?
Yes.
Is this all your work, or
no.
are you saying maybe?
So this is, at this point, so the first part is about the project as a whole. I definitely contributed to the project, and especially to Breeze. Like I was one of the main designers of Breeze, and I participated in like all the meetings for designing these things as well. And this co-design thing. But I'm not a hardware designer though. I'm just telling you to give you some background about where what I'll present next sits in the whole thing.
Can I ask about the size and complexity of the implementation of the hardware? Like, is it how many? Is there a lot of complexity hidden under this layer in the microcode or in the hardware?
Well, I think up to this point, things are quite easy. I think I have one more bullet, which is the complicated part. And it's all implemented in BlueSpec. So it's done by a couple of people. So it's not like most of the team works on designing hardware. I think the most interesting feature of the hardware is this programmable tag management unit. So a tag, you can think of it as an IFC label, although it's more general than that. But for this talk, you can think of a tag as secret or public or something like that. And every word has a tag with an arbitrary pointer. So if you have a 64-bit machine, you have 64 bits of payload for each word and 64 bits of pointer, which allow you to be very flexible about the kind of schemes you support, what this thing really does in the end. The operating system doesn't really interpret this pointer. All it does is on each instruction, say if you have a public integer and you try to add it to a secret integer, it's going to take the ALU is going to take the numbers and add them. And in parallel, this TMU is going to take the tag of the first integer and the tag of the second integer, look them up in a hardware rule cache. So addition of a public to or arithmetic operation of a public and the secret. And if it finds that in a hardware rule cache, it hits and it doesn't take any performance penalty. If it doesn't, it traps the software. And this is where this protection server comes into play, because then there is part of this operating system who needs to decide, well, is this operation allowed or not? And if it is allowed, what is the tag on the result? So if you add public plus secret, well, the result should be secret. And this allows to do fine-grained access control and dynamic information flow control at the lowest level, so at the system and hardware level, working together.
So how complicated things have you run on this? Because this looks like it's going to need to be implemented in the same sort of way as a TLB. And TLBs are TCAMs, which are very expensive. And on current systems, TLB misses are the main scalability bottleneck for compartmentalizing software. So if you're saying compartmentalize software using something that is implemented in the same way as a TLB, but you need more entries in it, that seems like the opposite of scalable compartmentalization.
Well, so at this point, we are not yet at the point at which we really have experiments to show what the impact of this. It can be indeed very big, especially since, well, trapping to software can be in thousands of instructions for an addition. Yeah? So the price to pay if you miss is very big. However, we also can use a big amount of the area for this cache. And there are some clever techniques the hardware guys are doing, like hashing and things like this, to make this work reasonable. We don't know yet if it does.
All of the discussion, right? You are saying one instruction, we can use all the area for this. If you use all the area for this, you lose the area for other things, right?
Well, on our FPGA, we are like using 30% of what the FPGA currently gives.
Are you talking about 100% space overhead, or are you managing it in some kind of?
Okay, so we are not concerned with space overhead. I mean, unless we really run out of FPGA.
But your notion of performance cannot be one instruction. We can use all the available die for this, right?
No, this is not our notion. I was trying to simplify. It's not that.
Okay, it's a gross oversimplification,
yes.
Right? Okay.
I just wanted to clarify, so you are consuming twice as much memory and twice as much memory bandwidth for every memory?
Yes. However, well, yes, for the tags. The pointers are encoded using a compact scheme which encodes base, bounds, and the pointer itself in just 64 bits. So fat pointers, that's why I call them low fat. For pointers, we don't have a real overhead on a 64-bit machine. For tags, we do.
Okay, so you only got 12 bits size left, or 8 bits of size left or something for how much you can address with one pointer?
No, we can address, I don't know, something like 2 to the 48 or something like that. We have some sort of, how do you call this, floating point-like encoding for pointers, where you have some fragmentation and something like that, but it's on the order of 1% or something. As far.
Binary body kind of thing, and you just represent the exponent and
yeah.
Yeah. Well, we lose a lot of space on that.
Our experiments show around 1%. The hardware guys' experiments show around 1%.
Wow. Okay.
They have a paper about it. I can point you to it. Okay, so that was about the architecture as a whole. Now some things I did, some research things I did. I also have done a lot of implementation and design and things like that, but this is like papers. So the first is about robust exception handling for sound, fine-grained, dynamic information flow control. Sound in the sense we get a security guarantee called non-interference, as opposed to just doing taint tracking and you don't get really any guarantee. Fine-grained in that we label each value and each component of a value separately. Dynamic in that it's a dynamic enforcement mechanism. And usually with such mechanisms, whenever I saw for the first time dynamic IFC, I was asking, okay, what do you do when something goes wrong? And this is what I'm tackling here. Since Breeze has such a mechanism, we wanted to do reliable error recovery in Breeze. And this implied that we wanted all exceptions, including information flow control violations, to be recoverable. And the problem is that existing techniques for dynamic information flow control, for sound, fine-grained dynamic information flow control, assume that you can just stop the machine whenever a fault happens. So something called stop the world failure. This makes some things easier, like you can get secrecy and integrity, but at the expense of availability. So in a real system, it's not conceivable that you just stop the machine whenever something goes wrong. So we wanted the information flow control exceptions to be recoverable. However, information flow control exceptions reveal information about labels. And it's well known labels are like, are runtime entities. They in a dynamic information flow control system, they're really attached to values and they flow in the system. It's not just something that happens in a type system or something. They're attached to runtime values. And it's well known in the literature that these labels can themselves leak information. And usually what you see in the literature is you can prevent secrets either from leaking into the labels or labels from being observable. And if you hide labels, you can allow labels to depend on secrets. And and this, in certain cases, gives you like more permissive enforcement mechanisms. There is even a paper by Austin and Flanagan called permissive dynamic information flow control.
This is no good, because presumably the labels are supposed to affect execution in some way. So as soon as you can affect execution, there's a channel, right? So isn't this a non-starter?
Well, indeed, this is a non-starter, and this is where I'm going to get.
Okay, we're done. It's a non-starter.
So I can show you a counterexample to it, or everybody agrees that it's a non-starter. So let me show you a counterexample to it. You have a secret bit, and you have three. So this S is labeled secret, but you have two more labels: public label and the top secret label. And you can encode the secret as a label, so you can branch on the secret and return always the same dummy value. But on the if branch, return the secret itself. Return something labeled secret. On the else branch, return something labeled top secret, something even more classified. And then we can assign this value to a high reference. It's like to a secret reference, sorry. And if you're on this branch, the assignment works. If you're on that branch, the assignment fails. And if exceptions are recoverable, if IFC exceptions are recoverable, then I suppose you can cache them and return different values when you cache them. So Simon was convinced from the start, but if labels must be hidden, then information flow control errors must be hidden too. And that's exactly what we don't want. We want to recover from them. So we have to prevent secrets from leaking into the label channel. So we have to enforce that labels don't depend on secrets. And this is the example I had before of branching on a secret and then choosing the label based on that secret. So what can you do with this example? How do you protect it? So the first solution, the solution for this problem is to use something we call brackets, which choose the label of the conditional before you actually branched. So it cannot be based on the secret. And if you choose wrong, then I'll explain later what happens. You get an exception, but it doesn't break anything. So the label you choose here, if you want both branches of the conditional to succeed, has to be above both secret here and top secret there. And then the secret is going to be topped up to top secret. So on both branches, you're going to get unit at top secret, and you won't have a leak. Now the second problem, which is not specific to information flow control errors, is general to all exceptions, is that, well, exceptions change the control flow graph quite significantly. And in particular, they interact very badly with this bracket construct. And this is how it works. So if you have a secret bracket in which you branch on a secret and then either throw an exception or do nothing, and then cache this exception in a public context, and return true if you caught an exception and false if you didn't, then, well, you've just leaked the secret. So throwing an exception from a secret context into a public context, well, this is bad. And this example shows why. So we cannot allow exceptions to propagate beyond that point, beyond the end of the bracket, which means we need to delay them, because we still need some information that something wrong happened. We cannot just swallow it or something like this. So brackets need to delay exceptions brackets need to be like a control flow join point, and in order for them to be sound. So now this example with the secret, if the secret is true, then we throw an exception. However, it gets delayed, and it gets labeled with secret. If you don't throw an exception, you get a unit because you didn't take the else branch. It gets tagged with, well, it's a success, whatever. And it gets labeled with secret. So now both things are labeled with secret, but now both things are values. We don't really want them to be values, and I'll return to this, but they need to behave like values. Similarly, when you have a failed bracket, and this is, I told you, I'm going to show you what happens when you mislabel a bracket. So this is the mislabeled bracket. You try to return 42 a top secret and then say, label that secret. You're going to get a value which is labeled secret as you asked. However, inside, it doesn't contain anything about what you wanted.
So I don't yet have in my head any kind of semantics for bracket. For labels and values, I kind of have the idea that if you've got a value labeled with one thing and you've got cells, references labeled with another, then you do a check when you assign them. That, I kind of vaguely get that. But so what's the semantics that you have in mind for these bracket things?
I didn't show you all the ingredients necessary for that semantics, but I can give you like a 1-minute explanation. So in dynamic information flow control systems, there is a notion of a PC label, or like a current context label, okay, which tracks under how many high branches you are. Yeah? So if you branch on a secret, your PC all of a sudden gets high. And then in the branches of a conditional, like when you branch here the PC is high. Okay. And what the bracket does is when you end the bracket, it restores the PC to what it was at the beginning of it. So it says this is the end of this high context. Let's say we are out of it.
It's basically treated like a scope.
It is a scope. It gives a scope for the, like you go high, you branch on secrets. At some point you have this control flow join point, and you say, okay, now I'm done branching on secrets. I can continue in the low context again. And that's what the brackets do. In previous systems without brackets, that happens automatically on all control flow join points. But they don't require that you give a label on all beginnings of things that eventually join, which means they cannot enforce this, they cannot have these sound public labels. They cannot have labels and IFC exceptions be observable in those systems.
So you're saying in the other systems, a conditional would implicitly affect the ambient level, and here your conditionals do not. Rather, only these brackets do instead.
Yes.
And that has an advantage. Okay, that's it.
So I mean, you could inline brackets. I mean, kind of have an if plus bracket construct, but then it will have to take a label. Then you would have to have a function call plus bracket and things like that. Yeah. So in the end, it takes this pattern and it gives you a general construct that does it soundly. Okay. So we need delayed exceptions. So they're somehow unavoidable, and I believe they're unavoidable. However, we still have a choice on how to propagate these delayed exceptions. And we looked at more alternatives, but there are two main ones. One is to have the normal Java-like or whatever-like Modula-like exceptions in which you mix active and delayed exceptions. So you have, when a division by zero happens, real exceptions gets thrown. When a bracket, at the end of the bracket, this exception gets delayed, becomes a value. And as soon as you touch that value, the exceptions gets rethrown, reactivated. So this is one thing you can do, and we study this mechanism. However, we have a more interesting mechanism, which only relies on delayed exceptions for exceptions handling. We call these delayed exceptions not the values, like not the numbers, but they're not quite the same. They're first-class replacement for values, They're propagated solely via the data flow. They're labeled, and they're pervasive. They can appear everywhere. And this is a simpler and more radical solution which we implement in Breeze. It's simpler because the other one also has delayed exceptions. It's just they also have the other ones. So what exactly is a nav? Or what does it contain? It contains debugging aids. So first, if you've divided by 0, you're going to be told that you've divided by 0. So it's more than a null. Even more, it remembers a stack trace at the point at which the nav was created, which is again different than nulls or things like that, which, well, if you get the stack trace, you get it at the point at which it dereferences it, which might be very far away. And you get the propagation trace, which shows you how the exceptions made it from the point it was created to the point where you touched it, or where you got to it, where you printed it, if you want. So this should help programmers understand, well, where these things come from and how they work. And however, we might not want to be fully precise in the semantics about things like error messages, stack traces, and propagation traces. So we might want, if you want to have a very efficient compilation, we might want to do the Haskell trick and have imprecise exceptions in which, well, maybe not all locations will appear in the propagation trace, or maybe the error message will be of another exception that could have been raised by that expression. So if you're willing to give that up, the compiler guys in our team, like Greg Morris, I think they can make this really efficient and simple in the compiler. Now, there is still something funny about this. There are still some choices one can do about navs. So if you add a nav to an integer, you're going to obtain the same nav with an extended propagation trace, labeled well by the join of the labels. However, for operations that don't really use the value, that just pass it around, I call them parametric on the slide, you have a choice. Yeah? So if you just apply a function to a nav, should this just bind the variable to the nav and continue? Or should this just return a nav? So this is something like nav lax, nav strict behavior. If you cons a nav to a list, should you get a list containing a nav, or should you get a nav? Or if you write to a reference, should the reference contain the nav, or should you just get a nav and the reference be unaffected? So you still have this choice about whether to be nav lax or nav strict. Yes, Gil?
If you add nav plus nav, then you construct new nav, including both somehow.
So no, it's the old nav. The only thing that changes is the propagation trace. It's going to record the location of the plus because it propagated.
No, the question is if you added two navs.
Two navs.
So each has their own propagation trace and their own source. Now you get a third nav, right?
Here is exactly where these imprecise exceptions could come into play. If you do imprecise exception, you get either. If you do precise, then we are in a left to right call by value language. You should get the first.
Oh, maybe you should get both.
Maybe you should get both.
Hey, it's a clean slate.
Well, so okay, now as language designer, we can choose between these two. The advantage of nav strict is that it reveals errors earlier, but the problem is that it introduces additional constraints to the information flow control mechanism, because if you do this, you're basically not executing the body of the function. So you have a new control flow branch going around the body of the function, not executing it, which means you're going to have to raise the PCE. I now explained what the PCE is. So it makes it harder for IFC. In fact, if you apply nav strictness everywhere, you get an exception mechanism which is very similar to exceptions, but which is completely useless in this setting, because as soon as you have a bracket and it restores the PC, your context is going to force and see, is this enough? And it's going to raise it back again. Which means brackets become completely useless in such a, if you would do nav strict anywhere. Additionally, if you're in a lazy language, you will also force the whole language to be strict. So it would also not work in a lazy language to be nav strict. So in Breeze, we allow the programmer to choose, in particular, the contract system allows to specify, do you want these functions to be strict in its argument or not? In the formal development, we just take navlax as the default and then have just one nav strict construct which branches, is this a nav or not? Now, we proved termination insensitive in Coq for a couple of calculi, one with navs, one with both delayed and active exceptions, and one just with brackets but without exceptions at all. And for the nav calculus, the proof is done with all the debugging aids. So even with all the debugging aids, you don't lose non-interference. And the proof is error sensitive in a sense, which we don't mix termination insensitive and error sensitive. We are clear that errors are separate from non-termination. Non-termination is hard to deal with, but errors we can deal with. And additionally, we provided translations between most of these languages, showing that they're interencodable, which at least to some extent gives some intuition that these things have equivalent expressive power. However, you can also look at which one is more complex and which one is simpler and things like this. And all of them are anyway whole program transformation, like the error monad encoding. So
you said that you introduced these navs for a reason, right? You said there's a problem, so we're going to do this navy thing. And now you seem to be saying, I don't quite know what these three things are, but you seem to be saying something without the navy stuff that was terribly important turns out to be equivalent.
Well, it's not quite equivalent. It's encodable with a full program transformation. In the same way, exceptions are encodable in a language without exceptions by a full program monadic transformation. This doesn't mean that exceptions are not useful, does it? I mean, these transformations are quite complicated. Do you want to write your program 10 times the size and work in the image of that transformation?
I see. So you're saying it's kind of interesting result.
It's theoretical result. It could also help, for instance, before we did the non-interference proof before we had this. So we did them for each language independently. If we had this result before and fully proved, not just quick checked, we could maybe just transfer non-interference results from one to the other. Okay, so summary, we can do exception handling even in the setting of sound, fine-grained dynamic information flow control systems. I presented two mechanisms where all errors are recoverable, even information flow control violations. The necessary ingredients for this are sound public labels and delayed exceptions. And I really want to stress this necessary. I think maybe it didn't come across in this talk, but we really believe that you cannot do it without these things. That you're really forced to have something like this, either navs or the other kind of things we investigate. And it's a quite radical design. I mean, none of this is compatible with JavaScript, what most people look at when they talk about dynamic information flow control. It would require changing the semantics of the language. It's not something you can do without touching the language. And we believe that this is applicable also to static information flow control settings, especially the idea of delayed exceptions. There are many papers which do quite horrible hacks to recover precision in the control flow graph which was lost because of exceptions. In fact, there are also case studies that show that when an information flow control type system fails, or such tools fail, most of the time they fail because of exceptions. They fail to type check the program, yeah, because of imprecision, and the program is still correct. So if they were to do something like delayed exceptions, then they just avoid that problem, but they might need to change their language. Now, the third part of my talk, I'm going to tell you about this recent work on testing non-interference using quick check. So this protection server, so the piece of code that gets called when the TMU misses in that cache, in that hardware rule cache, is the most security critical and novel component of our architecture. So it's the best target for verification. And again, verification in the broadest sense. So the idea is we want to have the real machine running this protection server and prove non-interference for it, or some other security property. But in this talk, I'm focusing on non-interference. So we want to prove non-interference of a real machine running this real piece of code. And we do this by designing an abstract machine that does dynamic information flow control magically, like part of its semantics, and acts as an executable specification for this piece of code. And then prove non-interference for this abstract machine, correctness for the protection server with respect to the executable specification, and then hopefully put these two pieces together and show non-interference of the real machine running the real software. Now, I'm only going to talk about that part. And the question is, can we quick check an abstract machine for non-interference? Can we check the non-interference of an abstract machine? And another thing which I didn't mention yet is this more. This is part of a much bigger stack of more abstract or more concrete machine, which would be necessary if you were to prove the security of the whole thing. So here you might have intermediate languages of the compiler or something. And here you might have things like that abstract or that implement the allocator or the garbage collector or even lower pieces of the system. So, however, we just focus on this one slice of the cake, the abstract machine which acts as an executable specification for the dynamic information flow control mechanism. So now quick check is a property-based random testing tool for Haskell. And so can we use that to verify this property? Now, yes, and we've done it for a very simple machine, which we call the Pico machine. It's a simple stack machine with 10 instructions, and they fit on a line. I don't think I need to explain them. Designing a machine, even a 10 instructions machine with dynamic information flow control is tricky. I don't have time to really explain this, but things like this no sensitive upgrade done on stores, well, published in 2009. So it's not yet quite the state of the art, but it's not very far behind the state of the art in what the information flow control people do. So this is a very simple machine, so we could prove non-interference for this machine in 1 week in Coq. So you might wonder, why bother? However, we hope that quick check will scale better than Coq for doing the real thing, which, well, has 10 times the number of instructions, but Benjamin was doing a like back of the envelope calculation is like 1,000 times more complex. So if this 1 week is multiplied by 1,000, then that's already too much for us. But we hope that with quick check we can do it faster.
Is it surprising that you can quick check it? I mean, it's like asking, can you test software, right?
Well, so first, non-interference is not the simplest property you can imagine. Sure. So there is something about the property. And second, there is something about the degree of confidence in finding bugs. Sure, you can throw tests at a piece of code, and if it doesn't find anything, be happy. But say you introduce bugs, how do you say, systematically, on purpose. Will this framework find them? So this is most of the things. Can you actually find all the bugs fast? Not just, well, can you run tests against a piece of software?
Is it fair to say that one reason this is a difficult test problem is because for a program with an input that is a few numbers, you can sort of randomly generate those numbers. But here, the thing you're trying to test is the space of all programs.
Yes.
All legal programs.
The pairs of all pairs of programs.
Right, so that's a very big space and a rather complicated one with
Yes.
lots of invalid programs. It's sparsely populated and very large.
Yes.
And that makes it a hard test case.
Yes.
Is that right?
Exactly.
Cool.
So you have like 4 or 5 minutes more.
Okay. So how do we do it? So first, I told you that we inject these bugs in order to test things. And we do 3 things. We have clever program generation strategies, which you have to believe me that they really improve things a lot. Like for these injected bugs, like an order of 1,000 or something, in how fast the bugs are found, or if they're found at all. Then we have shrinking of counterexamples. You don't want to present, I don't know, 100 instructions program when a 3 instructions program is enough to falsify the property. Especially if you're doing this during the design process where this counterexample really help you change the rules so that you get them right. And then we've noticed that testing stronger non-interference property improves testing quite a lot. And that's the part which I'm going to focus on. So we have these security properties. You don't need to know what they are. Just however, what you need to know is this is stronger than this one, which is stronger than that one, and that's also stronger than that one. And then we have some property. The weaker properties is what we actually want. In the case of successfully terminating or like looping forever programs. These are the properties which we can easily test, no intersection. And these are the programs we can hope to have inductive or co-inductive proofs for. So you see there is an intersection, well, an inclusion, and this thing is usually called unwinding conditions in the literature. So I'll skip what they are and just go to the experiments, which show that, well, stronger properties discover bugs much faster. And this is like even more bugs, an even more complex machine. Well, more. The other one was like 6 instructions, and this one is 10. The 10 I showed in front. So these are the properties like this is the strongest and this is the weakest. The weakest properties use the most sophisticated generation strategies we could find, while the strongest property use something either fully naive or, well, slightly better than naive. And again, we get almost a factor of 100 improvement in how fast we can find those bugs.
Were there any false positives?
No. So our machines have. So our machine has all these properties. We could actually prove this property in Cox. So.
On the previous slide, it might be that in order to guarantee the property for server loops or whatever, that the weaker properties are the ones you want. So it might be that a machine or a program that didn't satisfy these stronger properties was actually perfectly fine.
Yes, it could be that you can construct a machine which has the weaker but not the stronger property. I believe that machine will be quite weird, but our machine does have all properties. So, and I believe even our real machine has all properties. So,
Right. So the stronger property is good enough.
yes, so it's like the inductive invariant you would need in order to prove the weaker one. So, okay, I'm almost done. So this stronger property is very cool. I mean, it can find bugs in the order of milliseconds on the average, and well, almost milliseconds also on the worst case out of these 14 bugs.
Is this surprising? I mean, if you have a strong, of course, if you have a stronger property, you're going to find a bug faster, right? I mean, I guess that doesn't really surprise me.
Well, how much faster? It could be 0. or 1.2 times faster or something, while this shows like 100 times faster.
My dad can find bugs really fast. He's a very strong property.
Yeah. So well, you could say, sure, always use this very strong property. However, this property requires discovering stronger invariance than all the other properties. So I didn't show you the property, so it's hard to explain this. But in order, there is a trade-off in both. Well, proving that this implies that and that implies that, which we've already done. So you could say that's once and for all. But there is also a trade-off in using this property because you need stronger equivalences between states, which require you to discover invariance of your machine. Things like reachability and can be complicated invariance. So for this machine, they were very simple invariants. But I will know to tell you off the cuff now what the invariants are for the real safe machine and how complicated they are. They're probably very complicated. So which means, yes, if you have the right invariance, you can apply this property. And you would need to if you were to do a proof. So if you see this just as the first step towards a proof, then SSNI is the right property. However, if you just want to test things and you want to make sure to find some bugs, well, I think this might be the right one because it doesn't require stronger invariance and it still performs quite well.
Wait, are you saying to test it you needed to discover invariance?
Yes.
So quick check is discovering invariance.
Well, no, quick check is giving you counterexamples if you didn't find the right ones.
Okay, yeah.
So it can help you find the right invariants, but it still won't find them for you.
Do you need to even specify the property that you're trying to check for? Is that what you mean by invariance here?
Well, so this SNI property is parametric in the indistinguishability relation you use on states. And the indistinguishability relation you need for SSNI is different than the one you need for LLNI and everything above. It's much stronger. It's like the usual thing with strengthening the induction hypothesis. Yeah? So you need to strengthen the induction hypothesis before you can use it. Yes. Okay, I have two final slides. So first, I have lots of ongoing work on this project. The first bullet is about proofs for all of this. So we have the diagram I showed you with both the vertical and the non-interference property, the correctness and the security property. We have proofs for the Pico machine, and we are working on a slightly more advanced and interesting machine. And then there are lots of things which I might or might not do, depending on how much I still work on this project. Some future directions, I'm very interested in privacy and in security protocols and security applications which guarantee privacy, especially ones based on zero-knowledge proofs. So things like, zero-knowledge proofs allow you to do things like you can prove that you're over 18 years old without revealing your age by cryptographic, in a way that's not forgeable or. And this IDEMIX is an IBM project. uProof is a Microsoft project. So this seems quite a big upcoming technology which starts to get practical applications. Zero-knowledge proofs were quite expensive until recent advances. Something else I find interesting is applying this fine-grained access control and integrity protection to mobile devices. So that's all from my side. Thank you.
Maybe half very quick question, then we can take the rest.
Yeah.
Did you compare it to any other testing tools?
Well, we are not aware of any other testing tools for non-interference. We tried some experiments with...
But QuickCheck isn't a testing tool for non-interference.
No. I mean, we have this framework which we built for testing non-interference. There is no such framework, as far as I'm not aware of. So that we didn't have anything to directly compare against. We tried doing something similar with a symbolic execution-based tool called CLE, but it was able to find only the very simplest bugs and in a matter of minutes, while we find them in like a matter of milliseconds.
But no other, CLE is another example of like formal verification people move into testing, but there's like traditional testing techniques, right? So did you use any of like that? Like imagine Michael, for example, has a testing regime he uses. Did you use any of these like traditional testing techniques?
You mean like unit testing, or?
For example, yeah.
Well, I didn't show, but we are generating something on the order of 20,000 programs per second to test the property with. So we can, and we are working on good distributions and things like this. You can feed it 5 unit tests, but what will that tell you?
I don't know. Maybe it would tell you something. You didn't try.
The unit tests in general are as good as, are better than nothing. But compared to property-based random testing, I don't think they're on the same scale. Simon? Or? No? You had your hand.
Okay, maybe we should wrap up and thank the speaker again.
Yeah.